All right, good afternoon. I feel like we're a little one-sided today. A little bit. All right, so last time we were talking about gas transfer. Today we'll wrap that up and then talk, kind of have an intro to adsorption. Depending on how far we get, I will take, it's fine, it doesn't matter. A little more balance, okay. I will kind of pause wherever we get to, and then when I post your kind of homework lectures for next week, I'll include whatever notes from slides from last time and this matching lecture video file. I'll put those on Moodle for you to kind of start about the same spot where we left off. So that's my aim. So again, that'll be in my absence. I'm giving you 2 adsorption lectures to cover, probably the anything we don't cover about the one right now, and then the following one, and then on Thursday next week, so a week from today, you'll have a guest lecture. Okay, and that'll be a little bit of a preview to what we'll cover in the final section of the course. Okay, so that's the plan. Don't bother showing up here Tuesday unless you want to have like lecture time together and you feel like that, sure, whatever. But then do come on Thursday. Okay. All right. So last time we were going through these slides. My connection dropped, so I'm going to begin recording again. Maybe it stayed, I'm not sure. But hopefully that's fine. I'll have the recording regardless. Okay, so we talked about this case 1 scenario where bubbles are making their way through a liquid phase that is largely not changing. It's mixed, but it's not necessarily changing. And so we were kind of looking at the dynamics of that. How are we going to model this? And we came across several equations that we can derive based on the fact that bubbles at depth are going to be compressed by pressure. And we know we have certain considerations in terms of the ideal gas law, right? Pressure PV equals nRT is kind of a governing equation for quite many things when it comes to gas. So, for example, if we pressurize a bubble and, well, let's say we had a 1 mole worth of a bubble. If we were to put that in at standard temperature and pressure, 1 mole of a gas is, I think, 22.4 liters. So that'd be a very big bubble. Now, if we compress that and take the pressure, let's say 100 times bigger, well, if everything else remains the same, you have to shrink the volume by 100 times to make sure the right side of the equation still equals the left side of the equation, right? So if nRT stays constant, but you pressurize it to 1,000 atmospheres or 100 atmospheres, now suddenly your volume is 100 times smaller, right? So that's the deal. That same dynamic could happen to a bubble, so we can know something about the bubble volume by derivation. We know the pressure with depth simply by the P at depth is going to be P at the surface plus essentially the weight of the water on top of it, right? So that's where we get the pressure at some depth Z is equal to the pressure at the surface of the water plus the density of the liquid times the force of the gravity times the depth. Okay, so that's where we have our pressure measurement coming from. And accordingly, we can then say, well, the volume of a given bubble is going to change related to that because it will change when we keep the same nRT. The pressure and the volume together have to be constant. So then we get the volume changing according to how the pressure changes. So does that big picture make sense? Probably a little more sense than I made last time, hopefully. Well, hopefully it made sense last time too, but hopefully that's clear. So then, of course, we can get bubble diameter versus depth and bubble area versus depth because we know the volume's changing and bubbles tend to be spherical. Okay, so all of those are just geometry that follows the simple fact that pressure increases with depth. We can also relate volumetric gas flow because as we're measuring, or how we describe a gas flow, something like our standard cubic meter per hour, that considers some standard conditions. So if we set a standard 20 Celsius, could be 25, but I think this particular metric uses 20 and 1 atmosphere, then as you add depth of water above that, what the flow rate, volume of gas per time, will change because the volume has to change to account for the pressure. Okay, so in every single one of these cases, the volume is changing with pressure because of the ideal gas law, and therefore we have some equation that we can relate to the depth and density of our liquid. Okay, so that's what this entire table is getting at. All right, so moving from there, essentially what we want to do is have some practice, apply it, and we stopped last time in the middle of this problem. We had taken a look at the solutions for part A. Again, this problem, we have some diffusers at the bottom of a tank, and they have some surface area. And so there was a few questions about, well, what is the true air injection rate per unit floor area, let's say for a cubic meter. So what is the cubic meter of air per minute per square meter of floor area? So what is that SCMH? And so there was information given about the diffusers themselves, and then we said we had 3 diffusers per square meter. And so there's a lot of calculations we could do, and we took a look at that to get this flow rate, but then divide it by the square meter of floor space. So then, and we kind of, I think, got through that part, so we'll take a quick look at that again. But then the next question is, what are the average diameter, surface area, and volume of the bubbles in the tank? And estimate the surface area for this gas exchange, this AL, in the entire tank. Okay, so at that point, we'd need to consider the surface area of the bubbles that we got, and then do some calculation to figure out how many bubbles. All right, so we looked at part A, made some sense of it, and now we're at part B. We'll take a look at the solutions in a minute, but I wanted to challenge you to think about, okay, what exactly are we doing, and what does that equation look like? Maybe what I need to do is come back here and copy these for you as well. But give it a moment and consider, how would you approach this? What are the average diameter, surface area, and volume for the bubbles in the tank? And take a moment, because we'll look, the book solution has all the equations, has all that. It'll bring you back to that table, basically, that we were just looking at. But see if you can sketch in your mind what pieces of information it takes to get the diameter of a bubble. Okay, I think that would be useful so that you're connecting the dots between, all right, pressure, volume, how am I connecting the gas law to this stuff? So see if you can start from PV equals nRT, and from the concept that the pressure at some depth equals pressure at the surface plus the pressure increase with depth, which we said was the density of the water, or the liquid, times gravity times the depth. So it'll take maybe 5 minutes to strategize and then look at the book from there. is coming in from the career fair.
We got stuff in all.
Oh, funny. It's no problem. So we're taking a look, we did a little bit of a review of what we did last time, so feel free to catch up on that with the recording, but we're taking a look at part B of the problem we were working on last time. So as you get settled, just take a couple minutes to strategize how you would find answers to these. Now, the book has equations. We talked about the equations, but we should be able to find information about the bubbles given that we have some connection between the pressure and the depth. All right, so let's take a look. And before we reveal the solutions here, one thing that we recognize is we're given a bubble diameter at depth. So at the 4.5 meters deep, they're 1.2 millimeters in diameter, which is nice because it's good to have some place to start. And these diffusers, otherwise, it's like, well, how big of a bubble are they releasing? I don't know. So that gives us a starting point. And then we have to recognize, well, the question's asking for what is the average diameter, and that's going to be changing as the bubbles make their way higher and higher through the water column, right? So as the pressure drops, they should be increasing to some extent. So then perhaps we can take the difference between the bubble at the size of the bubble at the top and the size of the bubble at the bottom, and then get our answer there. Now we should also perhaps recognize that we're going to need a relationship between the bubble diameter and the volume, because it's our volume that's changing. It's not the diameter that changes with, I mean, the diameter has to change too, but it's the volume that we're tracking in terms of what's changing with depth. So when the volume changes, the diameter changes and the surface area changes. And so probably a good starting point would be to remind ourselves, well, the volume of a sphere is 3/4 pi r cubed. And if we convert that to diameter, that should be pi d cubed over 6. The surface area, actually, anybody have that on hand? I'm blanking on the formula for that. It'll probably be in the solutions, but we'll probably need that too so that we can calculate the average surface area, right? 6 over, well, that was, isn't that a derivation for the, but that was that surface area of a bubble or of all bubbles? I remember there was some derivation. But what's the surface area of a sphere? Pi d squared? 4 pi r squared. And so then if we take that pi over 2, so it's pi d squared then, because if we take pi r, excuse me. Yes, that one. Yeah. So doing the same conversion, right, but with squared. Okay, so those will probably come through and we need to account for those. Now that was it pi over 6 equation, that's coming from, I think, a calculation of the surface area of many bubbles in solution, combining more factors into it. So we did cover that, but I'm just talking about the volume or surface area of a sphere, right? The geometry. Okay, so let's take a look. So the book says, a little hard to read up there, the surface area and the volume of the bubbles when injected are, and it's going to just take these same equations, right? So we're going to take that 1.2 millimeters. We can get the area of 1 pi r squared, or pi d squared rather. So we're good there. Here's our pi d squared. Gives us our surface area. Volume pi d cubed over 6. So we have 4.52 square millimeters and 0.905 cubic millimeters for the at depth parameters, and we're given the 1.2. So solution goes on to say for systems with fairly shallow depth, less than 10 meters, there's an approximation that we can use. I didn't tell you about, but the books apparently has covered it by now, to say that we can essentially average. We can say instead of worrying about this pressure change and whether or not it's linear with depth, or like how to account for any deviations, we'll just take the depth in half and say, all right, to calculate the average bubble, we'll just take the size at half of the depth and call that good. So rather than calculate the diameter of the bubble at the surface and compare that at the bottom. We're just going to calculate the diameter at the middle. Now, you can imagine if you go really, really deep, things might get a little squirrely in terms of how small the bubbles are being forced or things like that. Probably bubbles will start having to merge together or something. Things are going to be a little different with a lot of depth, so this is going to be a shallow sort of a situation. I mean, 10 meters, that's pretty good depth. Like, you're not ever really going to snorkel deeper than that, for example. So I don't imagine we're going to engineer any systems deeper than that typically. Okay, so anyway, we're going to take that and say that should be acceptable. So the average diameter and surface area of the bubble in the tank could be given, therefore, by this equation. This is calling back to the equation we were looking at a moment ago, or like the stuff we were talking about a minute ago. And here we're comparing the z. This is 4.5 meters. And z over 2. So this is giving us what we know the pressure at the surface. So what we're seeing here is the pressure at the surface plus the pressure at depth divided by the pressure at the surface plus the pressure at the depth we want to calculate. So this is going to be a conversion factor from what this equation is doing is converting for us from the diameter that is at depth to the diameter that's less deep. That's the point of this equation. And I kind of wanted to try to elaborate on that. So this will be multiplied by the pressure at the diameter at the depth. So this guy is at diameter at 4.5. Okay, so that'll be the 1.2 times this kind of conversion thing to give us that ratio. It's going to actually take our geometry and account for it to give us this diameter conversion. So then we get 1.27 millimeters as the change. So everything we were beginning to talk about was just already captured into this. The math that we would have had to go if I gave you, several more hours to like really do this by hand and do all the derivations you needed by hand, just comes out to this thing, right? To make that comparison. But you could do that. So then the average surface area, here's going to be our pi r squared that we talked about, or pi d squared, excuse me. And since we already know how the diameter changed, then we can calculate that. Right, so if we know the diameter at the halfway point, then we can plug that in, get that. Likewise, the volume. Another way maybe we could have done it, or if we had to do it manually, maybe this would be the way to do it. So right now we're just using the equations that are already pretty much derived using this guy. But one way we could consider it is if we convert that initial diameter into a volume and then calculated, okay, how much does the volume have to change with PV equals nRT, then go backwards to calculate the diameter at the halfway point. That should be exactly the same because that process should be captured right here. Okay, so that's the deal. Okay, and it concludes saying, note that the bubble volume increases more than the bubble area, of course, because it depends on the diameter with a larger factor. And of course, the area more than the diameter. All right, does that make sense? Okay, so let's take a look at C. It says estimate the other surface area, AL, in the tank. And here's probably where that call out to what we talked about before shows up. So the AL here would be the surface area concentration in the system. So give a little bit of thought to that, what it means. How would you go about calculating it, given that we just did find the surface area, things like that. Just as an exercise to connect where you think this would be going. Okay, so in this case, again, we're probably taking a look at an equation that the book gave us, and that's just going to simplify things. In fact, I think we may have already touched on it. I don't remember exactly if that's applicable here, but essentially what we're wanting is some way to convert from the number of bubbles, if we can find such a thing, times the surface area of one bubble. And really that would be the number of bubbles per volume, right? And then this would give us a surface area per volume type of deal, right? So the way we might be able to get at the number of bubbles per volume would relate to what we know about the amount of gas we're pushing into the water and then the volume of the bubbles, right? So we'd have to, if we say we're pushing some amount of gas into the water, divide that by the volume of one bubble, we should get the number of bubbles. Okay, so I expect that we can at least find some hints of that type of approach here in the answer. Okay, so the value of AL is the gas/liquid interfacial area per unit volume of the liquid. The rate of bubble generation we can describe as N, the little dot over it, of bubbles per floor area can be computed from the gas flow rate per unit floor area and the volume of an individual bubble. Okay, so that's exactly like I was saying. We can, but they're putting it as a bubble generation rate, I guess. Okay, so that would give us, earlier we calculated some gas flow rate per square meter of floor. So that was something we calculated in part A. And then we have that volume of the bubble in from part B. So we can take the average bubble volume and just go ahead and use that. So the deal here is we kind of have to, again, reckon with the fact that the surface area is going to change as the bubbles change as they rise, right? So that becomes a little bit of a challenge, but we're just going to go ahead and do the average surface area. So we're going to use the average bubble size in conjunction with the amount of air we're pushing in here, okay? So that's the way we're overcoming that part, because technically we may have a different number of bubbles if we started with the bubbles at the bottom. Okay, so the average bubble diameter is found. We can estimate the rise velocity of bubbles with this diameter to be 30 centimeters per second. I don't think we talked about that, but that's something that that's not too hard to estimate. That value, if we ever need to do that kind of thing, we can do that with the derivation of buoyancy, the force of gravity versus force of drag versus buoyant force. That analysis turns out to give us a pretty simple equation for sedimentation, but it can also be used for bubble flotation. So that's the type of thing they probably use there. Let's not worry too much about that at the moment. And just continue reading what the book has to say about it, because I don't even know if that's how important that would be. So anyway, we'll just keep on reading and see what they're talking about. So therefore, the average residence time of the bubbles in the reactor is 450 centimeters. So 4.5 meters divided by that speed, or about 15 seconds. And the number of bubbles in the tank at any instant per square meter of floor area then would be this. Now, it feels to me like we should be able to just take the flow rate. Maybe the residence time wouldn't be important too. Yeah, I guess we have to know how long they're staying in there. Okay. I think we're probably not going to go there for exam. I don't remember if it's in there for the homework, but we could easily go there, and maybe we will later, but for the moment, let's not bother. Okay, for this problem though, since the tank is a depth of 4.5 meters, water volume can be expressed, of course, accordingly. And then we get essentially this calculation where we say we have some total volume, we have some number of bubbles per square meter fluxing through that volume, and we can ultimately find the area of the total area of the bubbles per total volume of the system and get our number, which comes out to be 30.6 per meter. That's a strange sounding unit, but it would be the same. So 30.6 per meter would be like saying square meters per cubic meter, right? Surface area per volume. Okay. All right. Make some sense? Good on that? Yeah, that's given right here. 4.5 meters should be 450 centimeters. They just converted it because they calculated the speed in centimeters. So in case you're curious, sometimes in sedimentation, we would use this equation. Settling velocity of a particle would be related to the acceleration due to gravity. The buoyancy of the particle, or in this case, a bubble, I'll just call it a bubble this time, minus the viscosity of the water. The density of the water, times the diameter of the bubble squared over 18 times the dynamic viscosity of the water. That is a force balanced that can get us there. And it should work just fine for sedimentation or flotation. It does assume spherical uniform particles, blah, blah, blah. So that's just a little aside. I'm pretty sure that's the type of thing that the U would have used to get that estimate. Like I said, we're not going to study that in this moment. But it's not too complicated. Okay, so last couple thoughts here. How do we then take our understanding of the gas transfer and put it into practice for examples like that one, where we can say, all right, here's the rate of change. Here's our mass balance. What exactly are we doing? So for these case 1 systems, bubbles flowing through a mixed liquid, we can set up the overall mass rate of change of that gas I. And if we look at it as the rate of change stored in the bubbles themselves, what we'll see is so we would have the advective input of I plus some dispersion, which we're going to count as 0. The rate at which I is formed inside the bubbles, we're not counting that either. We're not really having either. We're going to treat the the driving force of gas into or out of the bubble as the net advective input, plus the rate at which gas enters via gas transfer. So we'll have this driving force plus this guy over here. So those two components would kind of describe the input and output of gas into this bubble. And if we take a look at, let's say, an oxygen trend, how is oxygen trending in some reactor as we're doing a diffused aeration system, one of these case 1 systems, what we'll find is the oxygen concentration here. Of course, it will be increasing with time if we are bubbling air into it and it has some change. So for a solution that is initially undersaturated with respect to the gas phase, the concentration of dissolved gas in the liquid, we will find that eventually will reach some equilibrium, right? So if the real or the actual undersaturated value is here, when we're bubbling, it's always going to be heading up towards the ultimate equilibrium point, right? So the dashed line here is equilibrium for dissolved. And then the CG out, that would be the gas phase concentration of our incoming gas. So if we give it plenty of time as it's mixing, we will approach those. Okay, and then less gas is being taken out of the bubbles. So the gas leaving, so the bubbles that reach the surface of our tank, normally if they're transferring a lot of oxygen, they will have less oxygen than they started with. They start here, and if it's super deprived, then by the time they make it out, they only have this much oxygen. Okay, so this tracks pretty well because the change should, it should be a nice steady balance there. And the point is, okay, we have some rate at which the liquid, our solution in total, is gaining this oxygen. So I want to elaborate a bit on that, not to the extent that we are deriving these ourselves, but to understand where we go with this so that we can understand this type of situation and then put a little mass to it. Relate it to some of the simpler mass balances that we've looked at before. So, if we have a condition kind of like we were just looking at, where we have some relatively short residence time and it's not necessarily at steady state, there are ongoing changes in the system. We are aerating something so that it is becoming more and more oxygenated. That's kind of the case here. So we have the rate of change. We've described this before. Some constant times this differential between the equilibrium state and the actual state. Right? That's kind of our driving force. We can convert that into values with Cg, so the concentration in the gas phase, and also expand this to capture the entire volume and then put it into more of a flow rate type of situation. We could, of course, divide both sides by the volume to get it back to just the rate and have it as a volume, like instead of just calling it the K, call it the Q over V. Essentially the same deal. We can further derive and express these guys, the CGs, into concentrations of the liquid, and it's going to add in some math, right, to basically express gas phase concentrations we have to do the Henry's law stuff, right? We have to do some conversions and calculations. That brings in some Henry's law stuff. We can describe it also with the overall gas phase transfer. Essentially, we can take a look how the book goes and go from here to this equation. At the end of the day, we're still looking at that driving force of C, the concentration at equilibrium minus the concentration at current, with some other variables. And I'm really just pointing all of this out to show that in a minute we're going to look at a table where the value of this, certain ranges, this entire equation will simplify one way or the other. Okay, so if this were to be a very large number, then we have an exponent of a negative large number. That's very different than if it's a small number, and the exponent here will act very differently. Okay, so that's what I'm highlighting. We'll take it one step further and say, well, we can take this type of approach and we can ask ourselves, well, this is describing it as a rate. Well, couldn't we also put that as a dc dt and ultimately do some integration to get a function of concentration out of this? So if we were to work towards that here, we could get it into this form, which, since almost all of this stuff is constants, it kind of comes back to what we were initially describing. This is a K times CL at equilibrium minus CL actual. And if we are writing it up this way, and I guess we didn't really have to do the full circle, but looking at all these pieces, we can then find a way to estimate this based on what's going on in all this. Okay, so the deal is we often want to estimate or know this based on maybe some observations or maybe some other scenarios. Maybe it's we want to understand it. And so having a good understanding of what's happening inside here would be important. Because if this term goes to 0, for example, then really these pieces give us pretty much that k, right? So that would be quite impactful to know, to be able to look at it that way. So let's keep this in mind as we take a look forward. We will come back to that core concept. Now, what could we do to find that k? Well, if we took a gas transfer system and we know something about the equilibrium concentration, which we often do, right? We could do that with Henry's law. Then with an integration, we could essentially get, for a batch scenario, we could get something that looks very much like our first order batch kinetics, right? Natural log of C over C naught, plot that versus time. If you have a first order reaction, you'll have a linear plot. So in this case, we can do that, except we're going to take it as, instead of C or C naught, we're going to have, well, let me just say this. We could also plot natural log of C versus time and get a linear plot. So instead of ln of C, we're going to do the natural log of this CL star minus CL actual. Whereas CL actual is what changes. So this changes with time, just like C changes with time in a typical system where C is reacting. So it's almost exactly the same. We just have the extra constant in front of it with that equilibrium concentration of gas. Okay, so that integral analysis is coming accordingly. dC over something minus C will integrate into this, ultimately to the natural log of, instead of C over C naught, it's the constant minus C over the constant minus C naught. Okay, which kind of answers my question from a few lectures ago, about a month ago. Okay, we can do that with no problem. Okay, so then we can essentially linearize this by taking the natural log or keeping it as a natural log and find that k. Now that can be pretty handy. So we can find that from data. And if we take a look at a couple of limiting cases, we will have an understanding of what we can do or what can substitute in for k, this gas transfer coefficient, based on where we are in terms of this mess. So this mess is the overall gas transfer coefficient times the surface area concentration divided by the flow rate, the volumetric flow rate of the gas, times the Henry's law constant divided by the volume. So if that number is much larger than 1, then essentially this exponential term goes to 0. So if this is a big number, e to the negative big number is close to 0, right? So e is just 2.7 something. Take that to the power of negative 100, you have a very, very small number. It might as well be 0, right? So if that thing in our generic expression, which here's our generic expression, if this piece is large, if this piece is large, then this entire piece goes to 0. Okay, so then on the flip side, if it's a very small number, then e to the negative 0.01 or something becomes quite big. And it turns out that, well, we can kind of estimate k based on this So this exponential term essentially, let's see, e to the 0 is 1, right? So if we get this number to be a very small number, did I just do that backwards in my mind? No. If it's approaching 0, then the exponent is approaching 1. Like e to the 0 is 1. So given that, then the rate constant here is approaching just this, just that value. So that's the distinction. That's why we are taking a look at this. And if that was the case, we could simplify it into here. And then in each of these systems, we could write the overall rate given that particular condition as either this guy or this guy. All right, so I just wanted to highlight that. Hope I explained that correctly or clear enough. And you can see the books describing exactly that. Okay, does that make enough sense? So that we can imagine there are particular scenarios where we can simplify our general equation, that general mass balance. It's got a lot going on in it, one way or the other. But at the end of the day, they're both driven by the concentration difference between equilibrium and current. All right? Okay. So I think this is my last slide here. We can kind of take a look at how the rate constant for a given circumstance is changing with this volumetric flow rate times the gas constant divided by the volume. That's calling back to that, the way we're looking at the slides a moment ago. We can see how a rate constant would change with that as a changing parameter, and it changes linear for some time up until things start dropping off accordingly. Okay, so this is providing 3 different values of KL, AL. So these are the 3 different curves we're seeing. The slope defines points where this K is equal to QH divided by V. And then while it's linear, it's approximately equal that way. And then when we shift, we are entering the other limiting condition. Okay, so I think that's it for gas transfer, and we'll get started on adsorption. And by the way, I think that I'll probably would either give you plenty of equation sheet type of materials for those different equations, or possibly, if it feels better for everyone, maybe as a way to catch up on class time, but I think we're already taking care of that. I would consider doing like a take-home where you could go back to the book and say, oh, okay, well, where were we going with this one? I'll try to keep it in class because I think that just saves you a little bit of time, and just make sure it's clear and direct with which equations we actually are going to need to use for that. Okay, so adsorption. I want to start with some of the basics, some of the definitions. We're going to talk about adsorption as a method to essentially enact mass transfer. Right? We want to be able to either capture, or maybe sometimes capture and release, maybe sometimes just release stuff from an adsorbent material. Typically, of course, our context is generally for water treatment, but you could do it with many phases. Anytime you have a phase interface, you are potentially talking about adsorption. So you can have an air-water interface, you can have an air-solid, a water-solid interface. All these interfaces, anytime you have a surface what we're going to talk about is adsorption being something that is encountering that surface and sticking to it. And this is going to be a little bit like Velcro. If you've ever had like Velcro on your shoes or something, you know that you can put it on and it kind of sticks, but you could also rip it back off and it comes off, right? And usually there's not too much else that happens, and you could probably repeat that. So that's a good analogy for adsorption, because maybe it stays for some time, and maybe some of the particles that were on it could also leave. So we could have them arrive and eventually leave. Maybe if it's super sticky, maybe more will keep sticking until there's not much room for sticky stuff. So if you've ever got a lot of, I don't know, fuzz, dog hair, cat hair, something in your Velcro, you'll realize it's not so sticky because there's not so much space for the things to do the sticky, right? So you can clog up the surface. So there's some surface area that's important here. So we would call the adsorbent that solid surface on which something will stick. In fact, I don't know if there's any markers in here, but essentially our whiteboard is an adsorbent that when we have a marker, we are adding some marker dust to it. And then when we go to take an eraser, we've got a better adsorbent that takes all those little dusty particles and sticks them on here. So now when I pop that onto the wall or to my hand or shirt or whatever, why not? Well, it's pretty clean. Now we've got like some particles here. I don't know if you can see them, but they'll wash off. But that's the deal. It's fortunate for me, lucky me or lucky my shirt, that's not very dirty today. But that's the deal, right? That's the act of these particles. They're going to stick on something. Maybe they could come off. Maybe they could move. And that's why whiteboards are remarkable. Okay, sorry, this puns. I'm on a jam now. Okay. Like you can mark them again, remarkable. Okay. So then the adsorbate would be the particle, the molecule, whatever it is that is going to stick to the surface. So in our little drawing, this would be our adsorbent. And then these guys would be our adsorbate. Okay, a lot like we were talking about a few minutes ago with the gas scenario, we will often describe adsorbent materials for a surface area concentration. How much surface area do we have that is available for this type of interaction? Maybe you could even call it an equilibrium reaction. Things adsorbing, things desorbing. Usually we'll talk about this instead of a surface area per volume, usually we'll talk about it in surface area per mass. So this would look something like how many square meters per gram, how many milligrams per, how many centimeters per milligram, or something, square centimeters. So whatever the units, usually we're going to use a surface area per mass. And you'll find that, you can get some powdered activated carbon, and it has some rating of X number of square meters for every kilogram or every gram. And then okay, if I weigh out this much powder, then it's going to correspond to that much surface area that is potentially useful for an adsorption reaction. Okay, a few common materials. I've just named one of them, activated carbon. We'll talk a lot about that. That comes in two forms, granular or powdered. Granular meaning they're more like sand grains, something about that size. If you've ever had an aquarium with a little bubbler, sometimes there will be a little thing with black rocks in it. That's just activated carbon, granular activated carbon. The bubbles will flow through that, and it kind of draws some water through that, does some adsorption for you. My aquarium that I have right now is very silly, because you should be able to exchange that every now and then if you cared about actually keeping your water, if you cared about the adsorption action, because eventually they need to be recharged or replaced. But mine doesn't have any way to remove the thing, so they're just stuck there, and it's just more surface area for bacteria to grow and do their thing, which is still good. Anyway, powdered activated carbon would look a little more like this stuff. here, maybe we'll be able to get a little more, can see a little come off there. It would be finer, powdered, and you could add it to water. It would probably settle out fairly well, or you could filter it out very easily. But you would add it and stir it, have a lot of surface area, have some way to recover it, and it would just be a dispersion. Whereas granular, you'd typically flow water through it, allow it to pass by it. We can use metal oxides, especially aluminum and iron type of things. Many cases we'll see water treatment use intentionally adding aluminum or iron as a coagulant that will precipitate and start forming small solids, and those, as they're precipitating, they have a high surface area because they're small particles, and they can interact with certain things like natural organic matter and kind of pull them out of the water with them. And so that's one function in addition to all the stuff about coagulation. I think we'll talk more about that later. In addition to some of those other pieces just helping the sedimentation, they're also acting like an adsorbent. We can also sometimes grab some metals or other ions, so maybe some arsenate, copper, lead, maybe even chromate. So certain ones of these, perhaps their characteristics kind of catch, maybe adsorb some of the other contaminants around. There's also things called ion exchange resins. These, that's a picture here. These are pretty small beads typically. There would be some kind of polymer, and they have charged functionality within the polymer itself. And so what you do with them is you load them up with a bunch of ions like sodium, or you could do it, that would be for a cation exchange, or you do anion exchange, load them up with chloride or something. And then when they encounter some other ion, they tend towards releasing the smaller ion and grabbing up the larger, more densely charged ion. So like two sodiums would leave in the favor of one calcium arriving. And it's kind of doing an adsorption type of reaction with the ions. They can also be used to adsorb other things that are charged, and for the same principle. So those are technically would be within the class of adsorbates. And then you can use things like clays, especially zeolites, which is one of several aluminosilicates. Definitely viable options. And they will have properties to absorb certain materials. So with all of these, our interest is, will they have a favorable reaction with or interaction with some particle or some chemical that we're interested in removing? And if so, are they themselves robust? Are they going to stay there? And can we use them repeatedly, like we want our Velcro to be able to be used repeatedly, right? So that's kind of some of the pieces that we want to know or want to have about them. And of course, we also need them to have a high surface area. Very often we'll use activated carbon. So some examples here. And adsorption often finds really good use in taking a concentration of something to a very low level. We're going to understand that more as we go through the math of adsorption, but that's a real big function if you have some small amount of a contaminant and we want to get it to practically nothing. Adsorption is a great option for those types of scenarios. Okay, a little more on definitions. There is technically a difference between adsorption and absorption, with a B versus a D. Some languages don't have any distinction. Some of the other Latin-based languages will just have a B only and call them both absorption or something. We also use zorb, desorb, sorbate, sorbent, all of these things. For our scenario, we're always talking about adsorption. And you can think of it, because in English we have words that kind of relate. So adding, making an addition, is we're adding the particle to the surface. Whereas you can think of abduct, If you abduct something or someone, you are snatching it and taking it inside your van or sketchy whatever vehicle of choice. To abduct somebody or something, you're taking it with it. Okay? If aliens abduct you, as in the movies, it's always into the belly of their spaceship, right? They don't just stick you on the surface. That's not an alien abduction. You might be able to parachute away or something. I don't know why I'm so silly today. Anyway, adsorption, you could think of adduct as like the fancy scientific term. I don't even know if that has two Ds. And that would just be attaching a chemical bond, or we would call it a chemical adduct if it's sort of one moiety adding to something else. Okay, then we could have a few types of adsorption. So we're going to stick with adsorption, even though it can be described in a lot of ways. A lot of these pieces, the zorb, desorb, sorbate, sorbent, just bear with the literature or with the book or with me. That's just common language to use some of these. So desorb would be to go do the opposite of adsorb, right? To zorb would be the shorthand version of saying adsorb. And those would usually be technically used in technical jargon. So we could have physical adsorption, kind of a non-specific reaction, like the Velcro, right? Just kind of sticks on there a bit. We could have chemical adsorption. We might call it chemisorb. This is a little more site-specific. So if we think of a virus has very specific characteristics, molecules on its surface, so that it can, I would say almost intentionally by design, let's say, adsorb to a cell with the correct receptor. And then actions occur. When that happens, it will inject its DNA and so on. So certain things would be very site-specific. Enzymes, when a molecule encounters an enzyme and it's the right match, that would be a chemisorption type of reaction. Even if there's not chemical bonding there, we would maybe call that a chemisorption type of a deal. Okay, so we have a couple ways of adsorbing. We're going to talk about adsorption often with a parameter called adsorption density. So this will be a little bit like a concentration, but it's actually going to be the material adsorbed per amount of adsorbent. So yeah, it kind of a concentration, but not in the way we typically navigate concentrations with volumes. So this is going to be represented either as a lowercase, typically italicized q, or the uppercase gamma. Had to actually look that up to verify. I thought it was uppercase. Might just be tau, but no, that's gamma, uppercase. And maybe you already knew that. Anyway, so the difference here would be, is it on a basis of mass of adsorbent, or is it on the basis of surface area of adsorbent? Okay, so we can talk about adsorption either way, and this will be essentially the amount of our stuff per adsorbent. Amount of the adsorbate stuck to our adsorbent, giving us some kind of concentration type of thing. Okay, last little thing, that surface area, really we're talking about specific surface area where things can adsorb. So maybe we can estimate that, earlier we were estimating for the gas transfer stuff, the surface area based on geometry. More typically, we're going to have, even if we do have spherical granules, we're usually going to try to do something to them to make them even more porous, have tiny little holes in them. And then we're increasing the effective surface area where more stuff can attach and sit. So specific surface area, that's kind of how we will consider that. So we could think of a concentration of adsorbed material, milligrams of some species I per liter, and expressing it as a concentration that's adsorbed is a little weird, but we can do that. So in a given liter of water that has some some adsorbent in it, how much of our adsorbate is stuck on it, right? We can calculate that, but that would really be saying essentially Q, so our adsorption density, that's our milligrams of I per gram of solid, times the concentration of our solid in the solution. So what that'll do for us is ultimately we want milligrams of I per liter as our units. So we get milligrams I per grams solid and multiply that by gram solid over liters. Okay, so those should cancel. We should get our value up. So we can relate it that way. And we can also relate, as we'll see, this will probably wait for next time, but we can relate the solution concentration if we know how much we started with and we let our system get to equilibrium, then whatever concentration of our stuff in solution, that should drop if we're adsorbing some of it, and we can find that difference to know how much is now on the solid. Okay, that's actually usually the way we do that. Okay, so then last thing I want to highlight in terms of the definitions is we'll talk about adsorption isotherms all the time. This definition can refer to just simply the general relationship between how much stuff is adsorbing per, like what's the Q per how much adsorbent we add, or it can be a very specific mathematical relationship, which is either empirical or some derived relationship between the adsorbent and the adsorbate. There are several adsorption isotherms, two major ones that most people use as kind of a starting point, the Langmuir and the Freundlich. You could also imagine just maybe it's linear sometimes or close enough. So what this is showing is that adsorption density as we add more of our adsorbate. So if we increase the concentration of the stuff that we're trying to get rid of, we can imagine that more of it will be stuck on some surface. That relationship is not usually linear because usually when there's space, there's a lot of space to store stuff, it gets stuck on there really quickly. So if the Velcro is nice and clean and you rub it on your fuzzy floor carpet, it's going to get stuck with some stuff pretty quick at first. But later, not so fast. It takes a lot more rubbing around on the carpet or whatever. Okay, so there's a few different models. The Langmuir here, this is going to rely or depend on the max, Q max, so the max that you would ever reach, times some constant, times the concentration, divided by 1 plus that constant times the concentration. Whereas the Freundlich has some power. It's some constant, c to some power. So there's a few ways of looking at it. You're going to get different shapes. And we're pretty much out of time. I was mentioning this a moment ago. Let me just say, when we reach equilibrium, and we always have to reach equilibrium with these systems to really then study the isotherm. There could be dynamics we could consider non-steady state or like non-equilibrium, but we're going to reach equilibrium and then study our system. So the mass balance is preserved. So the mass of the adsorbate in the system initially is going to be equal to the mass of the adsorbate in the system at equilibrium. It's just where did the mass go? So if we started with no mass on the surface initially, then we can simply say, this is normal, right? This is usually, or this is with a clean sorbent. See, I did it already. Clean adsorbent. Then it would be a simple matter of saying the initial concentration is going to be equal to the concentration that is still in the liquid phase plus what's stuck on the surfaces. Pretty simple. I guess practically speaking, sometimes you might have something stuck to begin with, but a problem, we'd typically start with something new. I need to leave it there and have a good week next week. See you in a week and a half.